of today. So we have Sumiran Pujari from IIT Bombay. He's going to tell us about pseudocriticality in quantum spin chains.
Thank you very much. And hello, everyone. Thank you for hanging back for the last session. So yeah, today, maybe I'm a little bit of a stranger to this audience. So I come from IIT Bombay in Mumbai, India. And I've enjoyed greatly my time at YITP this last week. And also, I should firstly thank the organizers for this opportunity, and also thank my local host, Masaki Tezuka, and Kyoto Physics Department, where I'm hosted. I've spent last few weeks, and it's been really great. So thank you again. So let's move on. So today I'll be talking about quantum spin chains. We have heard several talks on quantum spin chains, and you see the word pseudocriticality in the title. So the canonical example is the Heisenberg spin chain, which is critical. So you can think it in that context, that I'll be talking about some spin chains which are not critical, but neither quite non-critical. So they're somewhere in between, which is why the word pseudocriticality. And one technical thing is, like, Heisenberg spin chain is described by a real CFT, complex conformal field theory, and there will be some complex CFTs appearing in my discussion. So, but before we move on, I just wanted to highlight one poster plug, even though the poster sessions are already done, and I hope some of you got to see. This is a different topic and result, which connects more directly to some of the themes that have been discussed in this conference related to eigenstate thermalization and so on. So the bottom line is there are these set of models that I had written down in the past, and I was interested in them because I could prove quantum spin liquidity in some sense, in some well-defined sense. And they have an interesting, if you wish, a many-body form of non-abelian symmetry algebra, which allowed me to prove those results. And they are very natural models. If you're familiar with bond-dependent Z2 symmetric spin half models, for example, like the Kitaev honeycomb model, these are in that class, but their physics is quite different and the symmetry properties are very different. And that leads to the spin liquidity that I mentioned. But it also, because it's, as I mentioned, it's a non-abelian symmetry, it also leads to degeneracies in the spectrum, across the spectrum. And the consequence is actually extensively many degenerate states. So one natural question that led me to wonder is to think about thermalization and eigenstate, thermalization type of questions. And the bottom line is, it's observation, we don't understand why, that we find thermalization, eigenstate thermalization, and even volume law entanglement across the many-body spectrum all the way down to the edges. It's mysterious why it is happening. It must have something to do with this many-body non-abelian symmetry that I just said in words. Somehow that is controlling the eigenstate structure enough to give these results. But if we'll be very happy for any feedback, and if anyone gets interested, we'll be happy to tell you more. Okay, so this work is done in collaboration with a postdoc who is also in the audience, Arnav Pushkar, and also my local host, Masaki Tezuka. Okay, so now we come back to the main topic. So as background, we all know that quantum critical phenomena is one of the organizing principles for strongly correlated matter. So quantum critical points give us a way of thinking in some coherent organizing way about the full phase diagram as phases emanating or arranged around your favorite quantum critical point. They also give us a way to think about the low energy excitation structures away from the quantum critical point. Of course, very interesting is that these critical points have scale invariance, and this you can get quantitative about it by computing, say, critical exponents and renorm RG understanding of all of this. So this is very nice. The setting for this talk are quantum spin chains, which are one of the simplest cases where you see quantum criticality. As I mentioned, the canonical example is spin half Heisenberg chain, which is a critical Luttinger liquid. It has, we all know this well, power law correlations and spin-on continuum physics that you can experimentally see in neutron scattering studies. And these are, at some level, consequence of the scale invariance. But spin chains are interesting because in 1+1 dimension systems, there's this powerful conformal structure. There are extra symmetries that actually constrain your physics in very strong ways, and you can make very strong predictions. And importantly for this talk, the conformal data, the CFT data, such as central charge and so on, control most of the physics in the problem, and you can sort of say a lot of things. So coming towards pseudocriticality, in the last decade, from my point of view, the notion of pseudocriticality has gained some prominence in the following sense. So this is in the context of the topic of deconfined quantum criticality in 2+1 dimensions. So this is a theory, a very quite elegant theory in this topic of quantum magnetism, and it allows for a sort of framework to have a continuous transition between two states of matter which are not symmetry related to each other, which is where we don't normally expect continuous phase transitions. But this theory allows for a coherent way of why to expect a continuous phase transition between two symmetry unrelated states. So the prototypical example is the nail state, which breaks SU2 rotation symmetry, and the valence bond solid state, which breaks lattice symmetries. And this was what the original proposal proposed. And this led to many numerical studies. People have tried to pinpoint the nature of this transition in various numerical lattice models. And presently, the consensus is that the observed it's not quite continuous to the best numerics, but they are very weakly first order. I mean, if you don't look too closely, you might even confuse it to be continuous. But when you look closely enough, you see that there is a slight sort of discontinuity. However, having said that, the general physics principles of this theory are most likely still operational in this transition, but it's a matter of perhaps detail why it is not exactly continuous. So one way in which this aspect shows up is if you do finite size scaling, you see critical exponents. The data can be collapsed nicely, order parameter data, but the critical exponents drift with system size, which you don't expect at a second order transition. And you may think of this very weakly first order behavior as some approximate scale invariance at some intermediate length scale, and therefore the critical exponents drift when you go away from that regime. So this observations actually spawned multiple interpretations. So one of the original sort of, it was actually a complaint or a gripe with the theory of deconfined criticality is that it may not be stable, just a theory may not be stable, and generically there might be runaway flows away from that fixed point. More recently, these sort of observations have spawned another interpretation, which is going to be relevant for our talk, where you think of the fixed point to be residing not in the space of real tuning parameters, but somehow you complexify the tuning parameter space, and the RG fixed point lives in that complexified tuning parameter space, but the real tuning parameter space happens to be close enough to that complex fixed point such that the RG flows actually impact the physics that you observe in your lattice model. And this is called as walking flows also in the literature, and it leads to a complex CFT description. So the CFT data is complex in some sense. There's a related alternate sort of interpretation where you analytically continue not in the tuning parameter space, but in the space of dimensions. You think of non-integer dimensions somehow. It's a similar idea, but applied differently. So in this talk, what we'll do is that we'll actually show quantitatively complex CFT behavior in quantum spin chains. So the background I gave was in 2+1 dimensional systems, but in 1+1 dimensional system, we can do it quite quantitatively and somewhat satisfying. And just as a note, in classical statistical physics, such weakly first order transitions are known in Potts model. If you go to Q greater than 4 Potts model, such behavior is known, but in quantum spin chains, perhaps this is our study demonstrates it. Okay, so what is the setting? So we'll look at spin chain models, lattice on the lattice. The lattice, the degree of freedom is SUN spins. So the familiar Heisenberg model, JS.S, SI.Sj, is the SU2 spin half version. And this structure can be generalized to SUN symmetry group. We have seen examples of this in this conference already. You can basically think of it as each lattice point. The Hilbert space is an n-dimensional Hilbert space. You attach a color or a flavor to each lattice point. And then there's a very simple quantum mechanics in this Hilbert space. You have these diagonal matrix elements that take you from alpha alpha to alpha alpha, or an off-diagonal matrix element which take you from alpha alpha one color to a different color, alpha alpha to beta beta. And SUN symmetry is ensured if all these matrix elements are of equal strength. So the two-color situation is the Heisenberg model. So for spin chains, there's some information known actually. So the n equals 2 case is the Heisenberg, which is gapless critical with central charge equals 1. It turns out the n equals 3 case is also related to a spin 1 model. So this is a spin 1 model, and the interaction, the SU3 spin chain is equivalent, can be mapped exactly to the biquadratic interaction term, if you're familiar with. So we have seen examples of this term in like when there was a discussion of AKLT chains. So this is one of the terms in the spin chain Hamiltonian. And it is known that this spin chain, biquadratic chain, is actually gapped. Okay, and in fact, for all integer n greater than 2, it is known, this was shown by Affleck, that actually you have a dimerized phase. They are gapped spin chains. So what's the point of this talk is that we are going to somehow argue that these gapped phases are these pseudocritical phases. Okay, so one kind of question you may ask is, how does the SUN spin chain go from being gapless or critical to being gapped at n equals 3? A priori, this question seems strange because n are supposed to be integers, and our take will be we'll sort of extend it such that n becomes a continuous variable, and then we can somehow show that this is as if there's a transition from this gapless phase to this gapped phase. Okay. Any questions? Okay. So this need not be said. Entanglement entropy and quantum criticality, we know their connections very well. So we'll be looking at Rényi entanglement entropies for technical reasons, because we can use numerical methods to measure them. In particular, the second order Rényi entanglement entropy. So ground state entanglement entropy, we know, is a probe of quantum criticality in some many-body system. So the known information, for example, is gapped non-critical systems follow the area law for bipartition entropy, entanglement entropy. And if you have a gapless system, you get universal corrections. And these universal corrections can encode information about the underlying CFT. So we will use this kind of universal corrections to extract CFT information in these spin chains. So we'll be making use of the famous Calabresi-Cardy relation. So this is in a spin chain. You look at the bipartite entanglement entropy. We'll be looking at it in presence of periodic boundary condition. This is the Calabresi-Cardy relation. The dominant term here turns out to be a log term. It scales logarithmically with the subsystem size. And the coefficient of the log term is where you can get the central charge, or the central charge of the CFT governs this log scaling of the entanglement entropy. You can get extra information from the subleading terms, but our focus will be on the log term. So for example, the transverse field Ising model at its critical point is the Ising CFT, and you can extract its central charge. For the Heisenberg chain, you have a central charge of 1, and you can extract it by doing these studies. I'll show an example of this. And as I mentioned, this subleading term is an oscillatory term for the Heisenberg chain, and it connects to the decay exponent of one of the CFT operators, and you can also extract that. So this is sort of our contribution, why our study was possible. We kind of came up with a method, a numerical method to how to do these computations. So even though this is the technical part, I'll just highlight the main points and then go to the results. So we use a Monte Carlo setup, which is called the stochastic series expansion method. So and this is all equilibrium statistical physics. So you take your partition function and you set up an expansion, like a Taylor series, a high temperature expansion. And at the end of the day, you write down an ensemble where each member of the ensemble, each configuration, you can represent it as a configuration of loops, colored loops. So for Heisenberg, this would be closely packed loops. So at each space-time point, there's a loop passes with a definite color or flavor. So for Heisenberg model, it would be just 2 colors, spin up, spin down. For n-spin SUN, you have n colors, and you have these closely packed loops. It turns out it's a kind of a happy accident that if you have bipartite lattices, the weights, when you recast the Hamiltonian, the partition function in this term, the weights are all positive or same sign. And then you can use Monte Carlo techniques to sample, and you can do things. And one extra step that we do is we resum over the color variables, which is possible to do if you have SUN symmetry. And then the ensemble becomes a collection of colorless because we invoke the colorful loops, colorless loop ensembles, again with positive weights. And the n factor enters as a parameter in the weight function of these configurations. And now once you recast the ensemble in this form, this n need not be integer anymore. You can take any real value of n and sample the partition function for any non-integer n. So that's our trick. To compute entanglement entropy needs a little bit of work. And I don't think there are any techniques to measure von Neumann entanglement entropy in QMC, but Rényi entanglement entropies can be computed using replica partition functions, which has been a very important tool in general for entanglement entropies, and we also use them. So we can skip the technical details, but you can recast the Rényi entanglement entropy as a ratio of 2 replica partition functions. And whenever you have these ratios of partition functions, you have some hope of setting up a Monte Carlo method to estimate ratios. There's a sort of hope to do something about it. And this is what is the main idea. There is one additional idea. So to measure this ratio, even though the ratio exists, whether you can sample it well is not a given, and you have to develop some algorithmic techniques how to do. And that connects nicely to the non-equilibrium theme of this conference. There's actually a trick to interpolate in some smooth sense between the two replica partition functions, such that this measurement is efficient. You can sample as you tune. And this is based on this Jarzynski equality type ideas. You sort of generalize the ensemble in some nice way so that you can interpolate, and then you can come up with an estimator that you can actually make progress to measure. But this is a technical detail. I'm interested. If anyone is interested, I'm more than happy to talk about it later. But this was actually led by a PhD student in my group and a postdoc from Tennessee. And really, this is the engine that makes all the results of this talk possible. And so now we'll start looking at the results. Okay. So I start with the familiar case of SU2 for system size chain length 48. And this is the red points are the measured data. So this is classic result. This is nothing new. This is well known in the literature. And there have been previous numerical studies which have seen this. We just sort of redid it. And the green line shows a fitting of that measured data, the red points, to this Calabresi-Cardi form. And as you can see, it fits very nicely with the measured data. So this form is actually the log form. For those in the know, they would recognize it. And these oscillations are these subleading oscillations, and you can extract the decay exponent. We are actually, this plot maybe undersells a little bit. The error bars are tighter, and the fit is actually better than how it appears. But it just works. Okay, so one curiosity is, as I said, since we are not restricted to integer n, we can make n any value. So we can make n non-integer less than 2. And this critical form, this Calabresi-Cardi form, actually continues to work for this situation. when n equals 1, the Hilbert space becomes one-dimensional. There's nothing there to entangle in a sense. So you get exactly 0. And you can even go below n equals 1. For numerical reasons, we can't go to negative n. I don't know how physical these are. Apparently, there are some connections in stat phys literature, but I'm not an expert. But the point is, when n is less than 2, the Calabresi-Cardy form continues to work, and it's gapless and critical. But the situation that I want to focus on is when n is greater than 2. So this is an example of n 2.4, where Affleck had argued that for any integer n greater than 2, you expect gapped. It should not be gapless. So n equals 2.4, the Calabresi-Cardy form continues to work rather well. And you start seeing deviations when n equals 3. I mean, eventually you will see deviations for any n greater than 2. But for the system size that I showed, L equals 48, you don't see any deviations for 2.4. But for n equals 3, you start seeing some deviations. And these deviations keep increasing. Just as a note, there is a regime where it still keeps fitting. The deviation is strongest in the middle for the biggest subsystem sizes. So this is the kind of mesoscopic regime that I have been sort of pointing at before, where the criticality is still working. For 3.6, the deviations become worse and worse, and eventually at some point, it just does not work. For n equals 4, it stops working. So this just recaps all of it in a single plot. The main message is that for n greater than 1, you have positive central charges. The coefficient of the fit of the log term is a positive number. When it is n is less than 1, you have negative numbers, and maybe that has some importance. But okay, now we go towards pseudocriticality. Let's first look at the critical situation. So I showed the examples for L equals 48. You can do it for different system sizes, and you can, yeah, sorry.
So for your fitting, you said you can get the C is a central charge this day. So I think you say C is a central charge and you get C is less than 0.
Mm-hmm.
So does this mean that your entropy formula is negative?
Yes, that's what it means. Yeah.
But based on definition, it should be positive.
Yeah. So this is you. So it's an ensemble. For us, it's just a statistical physics ensemble. And when you just measure this ratio of partition function, somehow the disconnected partition function has more weight than the connected partition function. And that's what you see. If there is a sort of interpretation, maybe from the point of view that you are thinking, that I don't know.
Okay.
But this is just the observation. Yes,
okay.
I agree.
Okay.
Maybe it's unphysical. Yeah.
Okay, thank you.
We just fit the data and we extract that. Okay, but we'll focus on the positive central charge regime. So you just repeat this procedure. You do the hard work, collect all the data, do the fitting. Then you study how the central charge behave as a function of the full system size. And for SU2, it just saturates nicely to the known C equals 1 value very soon. By 3248, it's already saturated to it, and the expectation is it just continues all the way to the thermodynamic limit. And this works for all values of n. All values of n less than 2. So it's described by a real CFT, if you wish, from the Calabresi-Cardy point of view. And furthermore, these dashed lines that I've shown are actually lines drawn from a theory prediction for what these central charges should be based on a Coulomb gas calculation for some loop ensemble in statistical physics literature. And the numbers that we see across n, we can match to this formula from the statistical physics literature. Now comes the pseudocritical part. So once n becomes bigger than 2, so for 2.2 and 2.4, as we saw earlier, the fit kind of kept working. And so if we follow the same protocol, actually, it looks as if it was what we saw earlier for n less than equal to 2. And the dashed line, the sort of the thermodynamic limit of this drifting central charge matches with the theory formula. And the theory formula actually gives complex values once n is greater than 2. Okay, and the value that you match is to the real part of this complex number predicted by this formula. So in our numerical simulations, the entanglement entropy sees the real part of this complex central charge. So now, but this is not the full story. Actually, what happens as the let's say the mismatch between the eventually the fit, the to Calabresi-Cardy relation starts breaking down once the system size and subsystem size keeps increasing, because it is actually a gapped system. And the way it manifests in the entanglement entropy is this extracted central charge starts drifting with system size. Okay, it's not kind of this plateau behavior, it drifts. This dashed line is again what is given by this formula. We'll come back to it very soon. And as n increases, the drift becomes stronger, and they just keep drifting. Eventually, even extracting a reliable C of L is maybe questionable, but we believe till I think n equals 3.6, we can reliably extract something that is meaningful perhaps. But it drifts, so it's nothing like a real CFT. But here's the clincher. There is actually a very nice drift formula that was derived by Han Ma and Yen-Chin He in this paper. So it's using concept from CFT, using the complex CFT-based RG flows of the coupling constants, and somehow that connects to the central charge, something called the C theorem. I'm not an expert, but they gave this formula to explain these drifts. That was really powerful for us, and we can actually fit these drifting central charges to this drift formula based on a complex CFT. And when we do the drift has this piece, this formula has this piece, which is the real part of the complex central charge. And we can actually recover this by doing this drift fitting, and it just works for this pseudocritical regime. Even though the system is not critical, this drift formula works rather well. And we can put it all together. This is what this agreement with this theoretical formula is what I showed before, but it really keeps extending wherever we can make the drift formula work. This it just keeps agreeing with this StatFist-based loop gas ensemble-based formula. So it is in this sense that I meant that we can quantitatively demonstrate complex CFT behavior in some gapped quantum spin chains. So there's one final curiosity, which is in the decay exponent. I didn't spend time on it. We seem to see that the Potts thermal exponent shows up in the decay. The subleading oscillatory term in these entanglement entropy contains the decay exponent. We numerically, and it's kind of a numerical observation that the decay exponent extracted in these studies matches the Potts thermal exponent and not something related to a Luttinger liquid parameter or something. So we don't know, it's just an observation. So that's it. This is my conclusion. So we believe that we have shown quantitatively complex CFT behavior in quantum spin chains. One important remark is this n equals 3 is the biquadratic spin 1 chain, which is dimerized. So it's a gapped state, but our study throws a new perspective on this kind of well-known phase diagram of the spin 1 chain. So if you remember, the Heisenberg spin 1 chain is the Haldane phase. But when the biquadratic term is the dominant term, you get this dimerized phase. And there's a standard quantum phase transition between the two with a central charge of 3/2. But once you go into this dimerized phase, we have evidence that this n equals 3 complex CFT actually governs the physics of the full dimerized phase. So that's one of the fallouts from our work. And in terms of outlook, maybe I can just highlight, for me, it would be very interesting, just as there were drift formulas for the central charge, if one could come up with drift formulas for scaling dimensions in the pseudocritical regime. that would be very nice. These drifting scaling exponents are also routinely observed in many quantum phase transition studies. So if there is a formula for that, that will be, I think, powerful. And finally, just to connect to the theme of this conference, maybe there are some implications of the pseudocritical states for hydrodynamics, maybe above the gap scale, but in this intermediate mesoscopic scale, I don't know. And perhaps if there could be a holographic derivation of the drifting central charge, that also would be interesting, I believe. So with that, I thank you for your attention. These are the two my collaborators who really made this study possible. So this is the reference. And I also thank my funding sources, in particular this grant, which has made my stay here possible. And thank you for your attention.
Any questions? I actually have a question. So I think I missed your explanation, but how do you simulate the fractional n?
So that is, so let me just go to that slide. So what we do is you just represent the original partition function as an ensemble of closely packed loops. And the weight of the loop is this weight function. And here n is purely a parameter.
Can I take large n to be negative? Does that make sense? Because
this n?
Yeah, large n, like the rank of the.
The large n, no, yeah. I mean, you can in principle take it negative, but from a Monte Carlo sampling point of view, it definitely becomes problematic.
I see. I don't know, I was just wondering.
It's defined. It's defined as a mathematical object.
I understand. I guess I was wondering, I had in mind like CPN model or something, or or Wen model or something. If you take n to minus n, there's something interesting about it.
There's some connections to Stratfus.
Right.
I know them, but we can't simulate it.
I understand. Thank you.
Yeah. I mean, for small negative n, you could still manage the sign problem. But once n becomes, I think the relevant ones are n equals -1 and -2, maybe. I don't know the details.
I guess also very large and negative n.
Oh, very large. That is probably.
No, okay, I understand. Thank you.
Okay.
Could you explain again why there's a big fluctuation for large n for entanglement entropy plots?
The drifting central charge?
Yeah. So I think n larger than 2, there's a big fluctuation. Is it? Yeah.
This oscillation you are talking about?
Well,
so this oscillation.
I think coming from sine, but for conformal field theory, there's no such a fluctuation, right?
No, for Heisenberg spin chain, I think even the CFT can derive.
Just coming from some lattice.
It is antiferromagnetic lattice oscillation, but I think CFT can capture this exponent also.
So bleeding French.
Yeah, there are ways to compute it also, but I'm not an expert.
Hello.
Yeah.
In your slide 8, it's a very basic question, but I just wanted to understand, how do you define AP and BP in the second line?
AP and BP. AP and BP, I think, where maybe I'll myself have to remind it. I think it was the bond index and the color index or something like that. But I can tell you the detail. It's like really nitty-gritty detail definition of the ensemble. Yeah, this has been a while, so I don't have it.
Any other questions? All right, let's listen to the speaker again.
Thank you.